Hello, my name is Cyrill Stachniss and I'm from the University of Bonn, and I would like to take you on a journey today and tell you how robotics technology can change agriculture. So which contribution can we make at the robotics community by deploying robots into the field towards more sustainable crop production? So if you think about agricultural robots, we have things like this in mind. These are systems that we as the robotics community have developed in order to operate on our fields, perceiving our fields, performing actions in our fields such as weeding or fertilization or other activities. And these are field management actions. And one of the things where robots can support us is to go new ways in terms of managing how we manage our fields that can be done in a more sustainable manner. First of all, I want to answer the why question here. Why should I care? Why should you as the audience listen to this talk and care about this? Why do crops matter? Crops matter because they're used for a lot of things which are important to us, like food, feed, fiber, and fuel. These are elements where crops play a very, very important role. And the demand that we have for producing them is increasing. This is due to an increasing world population, but also due to change in habits that we as humans have. So if you compare what we need to produce in terms of crops between 2010 and 2050, so within 40 years, that's approximately the same amount that we have produced from the beginning of mankind until 2010. And that's a huge amount. And furthermore, we need to do this in a sustainable manner so that also our future generations are not compromised by what we are doing today. And that's a big challenge. In crop production, we have challenges like this demand for a high yield that we need to satisfy. While at the same point in time, the arable land is limited as well as our natural resources, so we cannot simply scale it up. Furthermore, we are currently using a huge amount of agrochemicals in our fields, something that has negative impacts on our ecosystems. Last but not least, climate change doesn't make our life easier. It makes things less predictable. We have a higher uncertainty in our predictions, and crops typically need to be more resistant, for example, with respect to droughts or extreme weather conditions. And how can we actually achieve that? So all boils down to the important question of how to reduce a negative impact on our ecosystems while addressing the demand for a higher yield. And I want to highlight a few things where I think robots can make a change here. Before I dive into the robotics part, I want to tell you what are the two knobs that we can actually turn in order to improve this. So if you think about yield, how do we increase the yield? We can increase the yield by either having better crops or by caring better about our crops. And this is breeding, generating better crops, and improving crop management, so taking care about our crops in a better way. And here robots can play an important role because they can automate certain processes. If we think about the negative impacts on the ecosystems, we look here into the inputs. So what do we input into the agricultural system, such as fertilizers or herbicides or other agrochemicals? And again here, robots can play an important role by optimizing, for example, the management so that a smaller amount of chemicals needs to be applied, or that we supported breeding so that we have crops which are resistant with respect to certain diseases, for example, and thus need less chemicals that need to be applied to the fields. And also here, robotics can play an important role. So within the University of Bonn and the Research Center in Jülich, we have set up the Cluster of Excellence PhenoRob, Robotics and Phenotyping for Sustainable Crop Production. And here we are trying to study these problems. So we have people looking to digital technologies. These are people from robotics, from machine learning, from sensing, remote sensing, from mobile sensing systems which come together here. We have people trying to understand soil and plant growth, so people from phenotyping, soil scientists, plant modeling, and also modeling on a larger scale, modeling the ecosystem, modeling the dependencies that we have in economy in order to ship those systems in order to make a contribution in real-world applications. In my talk today, I want to look into the first element here, developing robots that support breeding and support field management actions, and that's what I will focus on for the next 15 minutes here. So how can we build robots towards more sustainable crop production? What do robots do? Robots typically monitor something and they execute certain actions or execute certain interventions. And these are things that we as roboticists know how to do, right? So we have solved perception problems since quite a while and then generated actions based on the models that we have learned. So in the end, we have a monitoring and intervention problem, perception action. So this perception action loop that we are using robotics since a long time plays an important role in here. And a lot of technologies that we have developed from robot perception and action generation can be applied to the domain here, may need to be adapted or optimized to certain settings, but I think we can actually make a substantial contribution here. So monitoring can be described with knowing what's going on, and intervention can be described with doing the right thing, given that we know what's going on. And I want to start with the monitoring part, and toward the end of my talk, look into the intervention part. So how do we do monitoring? What are we doing here? How do we monitor fields? We can drive with a robot over our fields and use our sensor data to observe the fields, or we take UAVs in order to monitor our fields. So this is an example for a standard out-of-the-box DJI drone equipped with a regular camera. And even with these rather cheap and inexpensive systems, we can actually perform a lot of monitoring activities. So what we need to do is we need to interpret the camera data. So how do we do that? How do we interpret our camera data if we work with a mobile robot? We take the camera data and we typically run, for example, a semantic segmentation system out there or a scene interpretation module. And we may want to run a SLAM system or bundle adjustment in order to build a map of the environment. And these are activities which pop up here as well. So the perception problem that we are addressing here for solving this field monitoring task is a semantic scene interpretation task coupled with estimating geometry, so bundle adjustment or SLAM, visual SLAM, for example. So let's see how that works in robotics. So in robotics, we use findings from machine learning and from computer vision, where we have this CNN-like structure where we put in our input images on one side and get our semantic annotated image as an output. So we basically, for every pixel, have a class associated to this, like whatever. That's a plant, that's soil, that's something else. And we use this in robotics all the time. So in autonomous driving, for example, we use this to interpret our surroundings, to estimate if there's a car in front of us, where the drivable surface. This is basically a semantic segmentation problem that we have. Or if we have robots which approach humans, they need to understand what are humans, and they can use these semantic segmentation systems in order to identify humans in the image data. Or in order to remove humans, for example, in context of mapping. If we build maps and we have humans running through the environment, we want to eliminate them from our data set. And that's something where these techniques play a role. So we can use this technology and adapt it to the crop domain. So if the input is an image of a field, we want to turn this into an annotated image, which says, for example, here green is a sugar beet plant and red is a wheat. And I want to get rid of all the red things, for example. We can use this out of the box and actually get a decent performance. We can, however, optimize this further, and we as humans have been dealing with crops since a lot of generations. So we as humans know that there are certain features which are valuable in order to distinguish crops, for example. So why not helping the computer and providing this as background information? So we've been looking into techniques to fuse an additional feature representation into those networks that we simply have a higher dimensional input, but that we do some pre-processing that we know that helps us humans, and let the network figure out if that's also helpful for doing the classification tasks in an automated fashion. And it turns out it helps and makes your system run in a more efficient manner. And these are some examples how we can do a crop wheat classification, or how we can use it in a vineyard to estimate harvest and optimize this approach for that domain. So once we have this, once we fly with our UAV through our field, we can combine this also with a geometric map or an orthophoto and then label every pixel in this large visual map and say, okay, in this area, I see a lot of wheat, so there's a high wheat pressure. We may run wheat control over here. In other parts of the field, everything looks good, no action is needed, while in, again, another region, there's a very slow growth, so I may rethink my fertilization scheme and optimize for this setup here. And this is a very valuable information for farmers, but as well as for breeders, which, for example, monitor their plots. And as a result of this, we have founded a company called PhenoInspect, which provides services for monitoring fields using UAVs for farmers, for breeders, and provides different forms of analysis. So we can fly over a field like this breeding application plot here, and then build geometric maps of the environment, and we can actually zoom into these maps up to quite high level so that we see individual leaves. So in this example, it's a 2 millimeter ground sampling distance that we have here, and we can perform a lot of the analysis, even looking for diseases on these images, and then perform a very easy to do fully automated monitoring of those fields. This allows us to do things like weed mapping and weed control, but also for the breeding application, we can, for example, do emergence counting and analyze when crops emerge, which is important for evaluating species with respect to each others. We can do ear counting in the context of barley, wheat, or other activities, or just compare breeding plots with each other. These are a lot of activities that help breeders to make better decisions later on. We can also look into 3D models. So if we have 3D data, like the data here from a laser rangefinder, in this example from a tomato plant, scanned at different days, we can actually analyze the growth of that plant using this data. And already from that point cloud, you see that is actually something that we as roboticists also know how to do, right? This looks like something related to ICP or SLAM, laser-based SLAM. And that's actually the case. It has different flavors and different challenges in there, but we can reuse a lot of the technologies that we have developed in the past. So if we, for example, want to register these point clouds that we see here with each other, different point clouds over time, that's challenging because the point clouds change their appearance substantially because the plant is growing all the time, the topology even changes. So let's say we have a point cloud of a plant at a certain point in time, and let's say we fit a skeleton in here to simplify our problem in the first round, and then we get a second skeleton, and now we want to align those skeletons with each other. So we need to find the data association between the points in point cloud number 1 or skeleton number 1 and those in point cloud number 2. And this problem here is typically a bit more challenging than what we experience, at least in 99% of the cases in the robotics community. And so we may rethink our ways for computing data associations. And we have developed special schemes optimized for plants based on hidden Markov models, which try to optimize the data association, taking into account that the plant can actually grow. And then we have this data association and can register those point clouds with each other. We say, hey, isn't that thing exactly the same as graph-based SLAM? And yes, it is very similar. It's not the same, but it is similar. So consider we have two skeletons, the blue one and the green one shown over here, and the red lines are here data associations. Then this is something like two post graphs built by two robots exploring an environment, right? And so the techniques that we use are very similar to what we use when building maps with laser range scanners in dynamic environments, although the dynamics are more challenging than what we typically find in robotics. So if you think about the techniques that we have developed, for example, for building 3D LiDAR maps in the context of autonomous driving, so that's some work that has happened in my lab in the last years, building high-resolution 3D point cloud data, then we can use this technology. We need to change it a bit, but we can use a substantial amount in order to solve the problem that we have here. Coming back to this example of the plant and the alignment of the post graph with each other, the underlying optimization problem is very similar to graph-based SLAM optimization. A difference is that we don't have rigid body transformations between nodes, but now a fine transformation, taking the scaling into account. But we also have other energy terms taking into account the correspondencies in a different way, or using plant-specific regularization terms, or taking some smoothness assumptions into account in these functions. And these are things that I can take into account in order to optimize the process and come up with better models. So that we can register point clouds with each other, overlay them, and analyze the growth even down to individual organs. So what you see here in this animation is the growth of the plant over time. So the red point cloud in the middle is our computation, our interpolation or even extrapolation of the crop, and the point clouds which come in from the side are actually our measurements. So at the point in time of the measurements, they perfectly overlap, but then we can actually morph one point cloud into the other point cloud, estimating and tracking the growth of the plant over time. And we cannot do this only for the plant itself, we can actually do this for every organ. So by tracking those organs, we can see when there are certain emergence of new organs and how the organs grow over time. And we can actually track this growth over time and derive phenotypical parameters from that, which helps breeders to make better decisions. This was the monitoring part that I covered. And the second part, I want to look into the intervention part. So from knowing what's going on towards doing the right thing. So moving over here. So what we want to do is we want to use the knowledge that we have gained from our monitoring and derive proper actions from that. So again, we have, for example, our plant classification system, which separates the crop that I'm looking into or that have planted and weeds, and maybe I want to do weeding, so I want to eliminate the weeds, so get rid of all those red pixels over here in my image. Then there are different ways, different techniques how I can do this. I can use spraying, spot spraying, just spraying the wheat plants, and this way reduce the amount of agrochemicals that I need. Or I may use a mechanical treatment, stamping, or using a hoe, or even other new technologies for reducing the impact that I need to put into the system. So this is an example of an agricultural robot that we have built together with other partners from the University of Freiburg, ETH Zurich, CNRS, University of Rome, Bosch, Deep Field Robotics, in the context of the EU project Flourish, and which we use in order to monitor the field and then run intervention actions. In this example, spot spraying and stamping applications that it can execute. But we can also go new ways and, for example, mount a laser on those systems and burn away weeds. So this is again just happening in a laboratory that's not on the field yet, but we can direct a high power laser onto a plant and basically burn the wheat plant away using this technology, so we can do weed control in a chemical free way. Just one of the things or ways that we are exploring at the moment. If we do this, we may also want to learn how to treat which type of plants. So if some plants are larger, stamping doesn't work anymore, then we want to spray it. Grass weeds should be sprayed all the time. And so I can make different decisions on how to treat different plants, from spraying, from burning, from stamping. And this is something that I can also learn. I can very precisely combine geometric features with semantic features in order to pinpoint also to the right location where I should execute my action. And that's something that our robots can learn and then execute already today. One of the challenges are still the varying field conditions. So if I'm on a field today and in 1 year, the field will look substantially different. Also, loading a classifier here and shipping it to Stuttgart or Zurich will not work very well because the conditions will have changed dramatically between the fields. Also between species, weeds and all the things. So we observed often a bad generalization performance if we train on field A and then move to a test field B. So one of the questions, how can we actually improve this without generating a lot of new training data? And one of the things we can do is exploiting prior information. In the easiest case, geometric prior. So if we know where the crop rows are, or not even where the crop rows are, but that the crop rows exist, we can try to find them and use this as a prior and retrain our classifiers. And there are other priors I can exist, and transfer learning also plays an important role here in order to generalize over different fields, over different crops and treatment methods, so that we can optimize our robots in terms of their perception capabilities and action capabilities. And still, there's a lot of work that needs to be done, and offers a lot of interesting problems from my perspective. But given this, then we can do, without retraining or with only doing the retraining in an unsupervised way, increase the generalization performance of the system here and provide a well-working robot. So what I have talked so far was mainly weeding from the application point of view, but there are other management actions such as fertilization or dealing with plant diseases, which are more challenging to address because you need a bigger background knowledge from the agricultural domain, more model knowledge because they are harder to observe. But still, there are a lot of interesting challenges that we can focus on so that you will be busy with these research problems for a long time. That's at least my prediction. So, in order to sum up and come towards the end of my talk, I hope I have illustrated here that robots can make a change to crop production and agriculture, and they can be a revolution in agriculture by optimizing monitoring and intervention and treating every plant individually if that's needed. It typically requires, however, that we as roboticists team up with people from agriculture to get the proper domain experts on board to build high-performing systems, at least if you want to deploy them in reality. There are still a lot of open questions and a lot of challenges that we need to address, but this all leads to applications which are of high relevance to our society and are very rewarding to work with. With this, I would like to come to the end of my talk. I thank you very much for your attention. I thank the Cluster of Excellence PhenoRob for all the support and the work I can do there with all the great colleagues at the University of Bonn, but also my team, especially my postdocs and PhD students who have done an outstanding job supporting me in my research, and without them I wouldn't be standing here and giving this talk. So thank you very much for that. Last but not least, a short advertisement. We are setting up a new conference in fall this year on digital technology for sustainable crop production. It's 100% virtual, it's free of charge. So if I stimulated your interest, feel free to join in and learn something about the robotics part of it, but also other parts, so that we can hopefully grow the community that works on these relevant problems. So thank you very much for your attention. I hope you will have a nice remaining ICRA conference and have a good time. Thank you very much.